Yes. Globally, yes. Going international. Hello. Today we're going to talk about the problem with cross-chain governance. I'm Odysseas from Nomad, which is a generic cross-chain communication protocol. We're going to set up a basic glossary, talk about Nomad and who we are, a short introduction into interoperability, the problem with cross-chain governance. Then we're going to dive into a bit how Nomad works as a protocol, why we think that cross-chain governance with Nomad makes sense, and I'm going to finish off with a couple of resources and the conclusion. First, what we say about cross-chain? What's cross-chain? What's cross-domain? Basically, we reference the communication between different blockchains that are interconnected in a way that make sense, in a way where applications can meaningfully communicate with one another among different domains. Nomad is an optimistic system. We're going to talk about that later. But basically, what an optimistic system is that we assume always that the system works as expected, and only if fraud happens, we believe, we hope that a good actor will tell the system that fraud happened, and then the system will roll back in order to remove that fraud. And when we talk about governance, we don't talk about multisigs or anything like that. We've reference to protocols that are governed by a DAO, where token voters can use their tokens to vote, and the result of the vote is direct code execution. For example, like MakerDAO, where a proposal is passed, code is executed to change some aspect of Maker. We will talk a lot about Merkle trees, so let's do a quick introduction for those who doesn't know what Merkle trees is. It's basically a very simple way to showcase that something belongs to a larger set. We have basically the hash of a message, and or a lot of messages. We don't care. Let's say we have one message, and then we do hashes of the messages, and we do the hash of the hashes, and we create a tree-like structure until we reach a root. So right now, with a single root, we have a very easy way to prove that something belongs to that set, because that information exists in the tree. Now, if we want to add a new message to that tree, we just add a new message, we do again all the hashes, and now the tree, the root of the tree has changed. So this is a very easy way to do a massive compression of basically of data, because instead of giving you 10,000 messages to prove you that this message belongs to all that messages, I can give you the message that I want to prove, give you the hashes, and then you can do the hashing yourself and figure out the root. My name is Odysseas. I'm a protocol engineer in Nomad, and that's my Twitter. This work was largely spearheaded by Anna Carroll, who is protocol lead in Nomad. So most of that work has already been done to serve Nomad protocol itself, as we are a cross-chain protocol. So we needed a way to do cross-chain governance ourselves. Now, let's change a bit. Let's change pace. What's interop? Let's do a smart. Okay, cool. Yeah. So let's do a small introduction to interop. So at first we had multisigs. It was the very simple way to do interoperability. Basically, you have a bunch of people, a group of people that attest that something happened on one chain, and then they go to the other chain and say, okay, this happened. And you trust that this bunch of people are honest. Then we had validators, which is basically the same idea as multisigs, but let's add some economic incentive in that. For example, if a signatory in that multisig or the multisig fails, they do some bad things, maybe they lose some bond, maybe they lose some money, basically the same thing with just some economic incentives. The third way was optimistic, so that's Nomad. It's the only protocol out there that has the optimistic design, and basically it says that the system works as expected, and you have a multisig, or you have a validator, we call it updater, that sees that something happened on one chain and goes to the other chain and says, okay, this thing happened. But also we have a fraud-proof window. So basically we say that after the updater goes to the second chain, there is a period where someone can go to the chain and says, no, fraud happened, this is not correct. So we turned the system, the design on its head, and instead of trusting a multisig, you have to trust at least one person, like at least one honest player will tell that fraud happened. And the fourth phase, which is like the end game, it's light client. It's basically a way to verify the consensus of one chain into a smart contract or the consensus of another chain. For example, that's Cosmos, where every chain in the Cosmos ecosystem can verify the block headers from any other chain in the Cosmos ecosystem. That's great because it's very secure, very fast, but it's very complex, it's very costly. So maybe we'll reach a point where we have light clients everywhere, but at this point, probably the most pragmatic approach is the optimistic design. Cross-chain governance. Now we have an understanding of basically all the major design schools for cross-chain protocols. Let's talk about cross-chain governance. What's cross-chain governance? It's very simple. You have maker on Ethereum, right? You have the maker holders, they vote on the DAO to change the protocol. But now maker needs to exist another protocol. Follow the liquidity, basically. So what do? How do you propagate that proposal? How do you force the same change across other domains? There are numbers of different ways that protocols go about it, because all the protocols have this problem, because they see users in other domains. The first thing is to do some patchwork. Basically, you try to use existing bridges that exist. For example, Polygon to Ethereum has a native bridge by the Polygon team. So you try to do this patchwork, which doesn't really work. It's not maintainable. It's a lot of ad hoc scripts and work, and it's cheap, but it's not a long-term solution. Some other protocols try to do their roll of your own. Basically, they try to create their own cross-chain interoperability protocol within the protocol. It's like creating a startup within a startup. We think the problem is too great and too big for a protocol to solve as a side gig. Better designed than the patchwork, but again, it's hard to maintain. Just zip it, the easier from all approaches. Basically, you just, vote here, you reach a conclusion here, and then you have a multisig here, and you hope that the multisig owners will honor that, will honor the same decision and implement the same changes. It's basically LARPing. It's not a cross-chain governance. Nomad, what we propose is basically two parts. One part is you have a protocol, which is Nomad, which is, we think, very secure, and it's a generic protocol for cross-chain messaging. And on top of that, every DAO creates a simple smart contract, the executor, which, when deployed, is configured to receive messages from the canonical chain and owns the protocol here. So this executor will always receive or always accept protocols that originate from here, and the protocol can only accept changes from here because it's owned by that. And the keyword here is standardization. We standardize the layer here, and we standardize the layer here. So now protocols have a very easy way to do cross-chain governance without having to solve a lot of problems. Let's see. We have a message from Ethereum, and then the relayer, which is an off-chain agent, which is trustless, anyone can later attest it to a new message, so it will take that message, we'll talk about it later, and go to Moonbeam, which is another chain. And then, if the watcher, fraud happened, then the processor, which is another change again. Yes. Let's see how many microphones will change until the end of this talk. Yes, so the processor will process the message and do whatever the message needs to be done. And this paradigm will follow if we want more messages to go from one domain to another. So it's 3 steps, and this is optional. The watcher will interject only if fraud happens and needs to shut off the system. To go a bit into more detail into how the protocol works, because I said message, because that's not correct. It's not a message that is sent through the protocol. It's a Merkle route. So let's see how that happens and why Merkle routes are very important to the protocol. So where the DAO votes for a proposal here, it goes to a router. Router it's not important, it's just, it's a user-defined contract that will take a user action and make it to comply to the Nomad protocol. And basically, it will go to home, which is the outbox for a domain, and say, hey, dispatch this message, some domain, doesn't matter. And the smart contract will just emit a special event. Now, this message is added to a queue of messages that are sent from home, but it's not yet sent. When the updater, which is an off-chain agent, it's bonded, it's the equivalent of a validator in other protocols, it will poll for events on home. And maybe it's one message, maybe it waits for a lot of messages, it wants to batch them together. It will, at some point, it will take all these messages and it will call the update function. Basically, what it does is that it empties the queue of messages and adds them to the Merkle tree. So every home, every outbox has a Merkle tree of messages that have been sent from that domain. And now, since they are added to the tree, you have a new route. So as I said, Merkle tree is a great way to compress information about something existing in a set. So now you have a new route for that tree. So you don't need to send every message through the protocol. The protocol just needs to make sure that the route will go from home, from the sending chain to the receiving chain. If the route goes there and lands there and in a secure way, then anyone can go to the receiving chain with a message and say, hey, this message belongs to that route. And since it can be proven on chain, the message will be processed, for example, sent to the recipient. So the protocol doesn't care to send messages per se, it sends routes. And that's ingenious, because instead of having to deal with hundreds of thousands of messages, you just send some small strings. And you know that if you do that correctly and efficiently and securely, then you can prove an arbitrary number of messages against that route, so you can send a lot of messages. So let's go back to this example. So yeah, the updater will call the update on home, so basically attesting that new messages have been sent from that domain. and a new update event will be emitted. And the relayer, which is an off-chain agent, will just read that update event and go to the replica, which is the receiving chain, and say, hey, I have a new route. You know, the sending chain has sent new messages, there is a new route, so you should get it. And a lot of people will ask me why the relayer works. You know, why should someone run the relayer? What's the cryptoeconomic incentive? And there is none. The incentive for running a relayer is that you care that the protocol works. You care that you want your messages to go from one domain to another fast enough. For example, you have a protocol, you have, I don't know, MakerDAO, you have Uniswap, and you want your governance, you know, proposals to go from one domain to another in a fast way. You care about it, so you run a relayer. It's cheap for you. You have an incentive, not a cryptoeconomic incentive, but an incentive in the protocol to work because you use it. And now the route has landed on the replica, on the inbox, and the window of time starts. On the happy path, there is no fraud, so no one will go to say that fraud happened, stop everything you do, fraud happened, the system should halt. So we're missing a line here, but that's okay. It's just a line. Yeah, the processor will check that the time has passed, which is another off-chain agent, another it's without incentive, cryptoeconomic incentive, that is. And then when the time passes, it will take all the messages that were sent, it knows about them from events, and will just start proving them against the route, the new route. Simple. And prove and process basically says prove the message and then process it. Process it means that send it. And in the Nomad protocol, in how we designed it, basically the replica will call the handle function. It expects that the recipient will implement a handle function with arbitrary logic. And that's it. So in our use case, the router is router and protocol. This is the user-defined contracts. So replica will call the handle in the governance, let's say, project we're talking about, and then the contracts knows what to do. In our case, it's an executor. So the executor will call handle in the executor contract, which implements the routing functionality, and it will read the proposal and it will execute it. Does it make sense up to this point? Awesome. So why choose Nomad governance? As I said, there are a lot of different ways to go about it. A lot of protocols have their solutions. I think Nomad is the best out there for two reasons. It's very good and very secure. It's probably one of the securest, if not the most secure solution out there. And it's relatively easy and simple. So you get a very nice equilibrium between difficulty and quality. The Nomad protocol is trust minimized and secure. As I said, you don't trust a validator set. You don't trust that any n of m people will be honest. Maybe that's great when you do 500 USDC amounts bridging between domains, but when you're MakerDAO and you want to execute a proposal that could have hundreds of millions of dollars in second order or third order effects, then you care that it's as secure as possible. And it's as secure as possible because it's trust minimized. You run your own watcher. You know that even if everything is malicious, the updater is malicious, everything goes wrong, your watcher will cut the system from performing a malicious transaction, so your funds are secure. It's low cost. It's a very simple protocol. As I said, we just care about passing arbitrary strings, the root. So it's very cheap relatively to light clients. It's simple, which means secure. It's very simple, very easy to implement in a lot of chains. We are only on EVM chains right now, but it's very easy to go to new chains when we have the capability to do so. And it has a bit of lag. It does. It's an optimistic protocol. We have to wait to see that fraud didn't happen. But that's maybe problematic when you want to bridge tokens. So you need to use liquidity layers on top of it, like Connext. They're a great partner with us, and basically they solve that, so we have everything. But like in protocols, in governance, you don't care about lag. You don't care if your proposal takes, I don't know, 30 minutes, 1 hour more, 2 hours more to execute. And the most succinct way to put it is, again, what do you trust? Do you trust to like a validator bridge, which basically some different people saying that they will be honest and be good players, but you don't know really. And the DAO trio, it's the same Pokemon underneath. It seems that they're different Pokemons, but it's the same Pokemon. And that means that it's a multisig of, I don't know, 15 of 30. But is it true 15 or 30? Do you really know that these, very big institutions own the address they say they do, or maybe it's less? You don't know. And again, maybe you don't care if you move smaller amounts or whatever, but when you're a big protocol and your proposal executions could have hundreds of millions of dollars in second and third order effects, liquidations and so on, you care. Or you care, or you have a water boy. It's simple. You care. You choose who to trust. You don't trust a random, unknown number of people to you, or known people that you don't know them personally. You trust only a single entity that you control. And you trust at least a single entity, to be more specific. You can have many watchers, but you need at least one, to be honest, for the system to work and be secure. To dive a bit into the water more specifically, the water does two things. It's part permissioned and part permissionless. And that's why we say that the apps choose who to trust, because it's up to an app to allow a watcher to watch over it. And what I mean by that is that the watcher, when it sees fraud, it will go to the sending chain and say, hey, this route was posted with the signature of the updater, but you don't have any record of it. And because the sending chain has all, it has a list of all the routes that have ever been generated. It knows all the messages that have ever been sent. It can see that, okay, the updater was fraudulent. The updater was malicious. That's the permissionless part. Anyone can do that. Anyone can post that proof. The permission part comes here. And basically, it says that the receiving chain has no way to verify if a message is fraudulent. It doesn't know all the messages that have ever been sent. So it trusts the watcher that if fraud happens, it will disconnect the application from receiving messages. And the trust comes to the part that if it was permissionless, anyone could run the function, anyone could halt the replica again and again and again, griefing no reason, because the replica, the receiving chain, has no way to verify fraud. So if fraud happens, it doesn't happen. Nope. Yes. So if fraud happens, let's see how a fraud would happen to understand the difference between being trustless and trusted. So you generate a malicious message, okay? A message that is fraudulent. You're the updater and you want to steal all the money from MakerDAO. You generate the message that would do that, that would allow you to, I don't know, withdraw all the collateral from a domain. And then you generate the route the new route. So you take the existing route, you take the new fraudulent message, you add it to that route, and you have a new route now. You are the updater. You can do that. And now you can call the update, as we saw before, that basically adds your, it updates the route, the existing route, to a new fraudulent route that would allow you to prove your fraudulent message, right, on home. Then, because the relayer works, it will relay your fraudulent route to replica, okay? It will relay your fraudulent route to replica. And then is when the watcher would kick in and would stop the system. So before you have any time while the fraudulent window is going on and you can't process the message, it would go to home and it would post fraud. So it would it would post the fraudulent route and say, hey, fraud happened. This updater was posted a route that didn't exist. And then it will disconnect, in this smart contract, it will disconnect your application from replica. So it will disconnect, the watcher will disconnect the applications that is watching over from the inbox. By disconnecting, it means that they can't receive messages. And that's why we said watcher is trusted. So every application, the system assumes that in every application, the watcher will disconnect that application from receiving messages. And in that way, the home contract knows about the updater can't post any new fraudulent routes. And since these applications have been disconnected from replica, even if after the time passes, they can't process the messages because the recipients have been disconnected. So they will try to process them, the malicious messages, and it will not be possible because the applications have been disconnected. And that's how a watcher would protect its application. A watcher can protect many applications. It's up to, we expect to see, for example, services where you're a protocol, you run your own watcher, but you also probably buy a watcher service for extra safety and liveness and so on. But that's the system, and it's very simple. And we move the power to the user, to the protocol, to decide who to trust. And that doesn't work. Awesome. So what choose Nomad governance? As I hinted before, it's a message passing protocol. We put a standardized executor. We partner with Gnosis Zodiac to do that. So it's very easy for DAOs to just deploy the executor and use the system to do cross-chain governance. Again, it's very easy and secure. That's what we try to be as, as hassle-free as possible. In conclusion, governance is way harder than it looks like. It's like surgery. It's necessary. Your protocol have to go where your users are, but it's better if you don't do it yourself. It's better if your protocol doesn't have to deal with it, and you just take a solution off the shelf. The right framework to think about it is that you should find a message passing protocol that covers your requirements. Maybe you care more about safety and security. Maybe you care more about speed. But the important part is to know your trade-offs and find the standardized interface, like the executor we talked about, because it's easy. Because you just deploy the interface, you put the protocol to be owned by that interface, and you're done. You don't have to deal with any of that. Nomad and Gnosis Zodiac is trust minimized and secure. It's cheap to use, the same old things. We talk about simplicity a lot because simplicity is security. If it's simple, if it's easy to reason about, it's secure. And of course, there is no silver bullets in bridging. There are no silver bullets in cross-chain communication. It's all about, trade-offs. Nomad is secure, but it has lag. Other protocols are more fast, but there is a trust assumption, for example, validator. So you should know the trade-offs. I'm a POS validator bridge, a continuity exists as I slowly shrink and transform into N of M multisig. My point is there's a lot of marketing speak in the area. It was, interop was a niche. Now it's coming slowly to the main stage. So it's important to try to go, over the marketing speak and really understand what are the assumptions and the trade-offs for your solution. Because if you don't do, someone else will do, and you will get a multi-million-dollar bridge. Most of the, the leaders in the Rect leaderboard in the paper, if you found, is bridges. There's a reason why, because they assume things that we shouldn't assume. Some resources, you can find the code here and play with the system. And thank you for your time. Now, if you have any questions, I think we have some time. Thank you. Yeah.
I didn't really get if Watcher is incentivized somehow to verify, or just launched as part of the applications, so no need to incentivize the Watcher additionally. Yeah, and if it still holds a legit message, is it slashed somehow or not? Yeah, and yeah, related question: this punishment of disconnecting, is it like forever or it just for a period of time? Yeah, yeah. Thank you.
Great questions. Thank you. Crypto economic incentives are hard. So a general design, approach is we try to eliminate it as much as possible. So we say the incentive of the Watcher is maybe it's out of band payment, maybe it's a service like running your own, you run a full node, an archival node, and you offer it as a service. And also, I will run my Watcher from my app. Maybe I'm a big chip, like I'm MakerDAO. I will run my own Watcher because I care for the system to work. I don't want to trust anyone. I want to trust my own Watcher, but perhaps there's a liveness failure. So that's why I will probably go out and buy a Watcher service as well, just to be sure. So generally, we try to go in a social layer consensus and use the social layer as much as possible, just because it's a rabbit hole to make an crypto economic incentive system. And
launch such Watcher. And, yeah.
It's very easy. We're finding our docs right now. It's very easy to self-serve and run your own Watcher, but obviously this is an open market. I expect the system to have like service, like big providers to offer Watcher service, because maybe you don't want to maintain your own operators, but you want to trust someone, and that someone will put their reputation at stake. So they can't, for example, grief you, because if they grief you, you will go out and say, I trusted the operator and they trolled me. So they don't have customers anymore.
Yeah. And actually, the only action...
Actually, that's a very good point, is that it's proven in a very famous paper in 2019 that it's impossible to have bridging without a trust assumption. So we are trying to move away from you trusting, we telling you who to trust, and having to trust some people being honest. And if they are not, you're screwed. If their keys are hacked, to you choosing who to trust, and you needing at least one honest player to be secure. But you need trust at some point in the system.
Thank you.
Yeah. So the only action Watcher can do is to veto specific change. So just discard it. He can't propose any other changes, but only block the existing one.
Exactly. The worst they can do, the worst is they will troll you by disconnecting your application from receiving, at which point you just change the water set. So they can't anymore interact with your application because you have removed them from the whitelist. And that's the same with like how do you reconnect, right? If fraud happens and the system holds, the system has a governance. So the Nomad governance will restart the system. We're working, it's an active research area because we have to remove the fraud from the system and then we have to restart the system. So this is something we will be working on now. We have some designs, but yeah. On your application, it's up to you to implement the logic on how the application can reconnect to the protocol.
Thank you.
Thank you. No more questions?
I had a question. Is it possible to have multiple watchers instead of a single one to reduce the possibility of fraud?
Yes.
So like have, for example, like 10, and if one is fraudulent, but the other 9 say otherwise, you...
Exactly.
Okay.
Exactly. The only point being that the more watchers you have, the more risk you have from griefing. But of course, if griefing happens, it's very easy for just to remove that watcher, so they can't interact with your protocol.
Okay. Thank you.
Yeah. Thank you.